कुछ घर चलेगी क्या बीच में? अच्छा, you guys have shifted the arrangements. Okay. All right. So we are starting this lecture, this second set of lectures on simplex. So initially we did derivation 1. Today we'll do derivation 2 and 3, and we'll finish the simplex derivation. We did an initialization. So what was the initialization part? We had given a B set and an N set. We had written last time that XB is equal to B inverse B, Xn is equal to 0, lambda is equal to B minus transpose CB, mu B is equal to 0, and mu N is equal to Cn minus N transpose lambda. So those who are watching the recording, we just discussed this for extensively for 15 minutes. How did we reach this? We reached this by following the three conditions which we said. The LP, the feasible region of an LP forms a feasible polytope. The second thing we said, the solution lies on the vertex of the feasible polytope. The third thing we said was the vertex maps to a basic feasible point. What was a basic feasible point? It is a feasible point Ax equal to B, x greater than or equal to 0. There exists R in B, there exists a B subset of the total n indices which contains R indices. The complement of B contains active constraints, and the matrix B formed from the columns of A matrix taking the indices from the B set is non-singular. Once we took that, we applied it to the 5 necessary and sufficient conditions, the 2 feasibility condition, the third Lagrange multiplier condition, the fourth complementarity condition, and the fifth non-negativity conditions. We got this initialization, and this we had done on an example to tell you how to initialize the simplex. In the problem also where we had stopped, you had got both the mu components to be negative. If all the mu components would have been greater than or equal to 0, your given basic feasible point would have been the solution of the linear program and you would have stopped. But now we have to do something about it, and that's where we are iterating. So we are saying if mu n is greater than or equal to 0, means all the indices of the mu, if they are greater than or equal to 0, then you stop. Else you choose a q belonging to the n set with where the mu q is negative. I mean, it could happen that all indices of mu's are not, mu n is not negative. It could be one is positive, one is negative, and so on and so forth. But pick an index, and if there are multiple index, pick any one. You can pick the first one, and then we follow certain steps. We said make in the new iterate, which I denoted by x plus, make x cube plus greater than or equal to 0. We said we cannot make this. Our goal is that we are somewhere on the one vertex of the basic feasible polytope, and we want to go to the next vertex. So this is your LP which you are working on. A is R cross n and R is less than n, and rest indices are clear. X is n dimensional, B is R dimensional, and so on and so forth. So make x cube plus greater than 0. We can't make it less than 0, because if we make it less than 0, we are breaking the feasibility condition of the basic feasible point. So this would imply, like Avril said, q goes to B. So to make your understanding better, I usually carry this example with me. Let's say the n was 5 and R was 3, and you had the n set, B set contains 1, 3, 5, and your n set contains 2, 4, 2 and 4, and let's say your q is equal to 2. The mu 2 turned out to be negative. I think in the problem which we did, both mu 2 and mu 4 were negative, I think. So you can pick any one last time which we did. So you pick mu 2. Now you're saying that once we are making the x cube plus greater than 0, we'll have to move it to the B set. So once we move it into the B set, how many indices does B contain? How many? R is 3, right? So now it will have 4 indices. So it will have r plus 1 indices. So again it's not going to the next vertex. It may go somewhere inside the feasible region on the boundary or somewhere anyways, we don't know, but we have to stick to the next vertex. So we have to ensure that it contains 3 indices only, or r indices, not r plus 1, which means that you'll have to pick an index from this and send it to the n set. Correct? So, so the next thing is B can have r indices. So we have to move an index out of the B set and into the n set. To move the index out of the B set into the n set, what will, let's say that index is q. Index, let's say p, from B set to the n set. Everybody agrees? This is what we'll have to do. So if you have to move an index from a p from the B to the n set, let's say that's the one index, what will happen to the xb plus xp plus? What will happen to xp plus? 0. Why? Because in the n set both the components have to be 0. The complement of the B set has to be 0, right? Then what else would you need? What else would you need? The new B is non-singular. This is the index set B and this is the B matrix, so don't get confused. So what we are trying to say is that now your new B, for example, becomes 2, 3, 5 after the swap, and we call this plus, so this is n plus and this is 1, 2. So this is 2, 3, 5. So from the A matrix you will pick the second column, the third column and the fifth column. So those columns, when you put it as a matrix together, that should remain non-singular, right? What else should happen? You are going from one vertex to the next vertex, one basic feasible point to the next basic feasible point. What were the 5 things to satisfy for a basic feasible point? Feasible, it should be feasible first of all, which we have not done, right? So it should be that AX should be equal to AX plus or, let me write it down, X plus the n set removed Q should remain 0 and XB plus complement of P should remain greater than equal to 0 and AX should remain as AX plus 1. Those are the 5 things which we have to do. Yes or no? What were the 5 things? First thing was the feasibility. This is the feasible part. I have written it in an opposite direction. We first write AX equal to B or AX is equal to AX plus 1. X was the earlier iterate before I did the swapping, and after I did the swapping I'm calling it as X plus. Is that okay? And then we are already working with XQ plus. We are making it greater than 0, which means that it has to go into the B set, which means that the remaining X components inside the X plus, they should remain equal to 0. So if earlier the components was 2 and 4 and you made x2 plus to be 0, the x plus 4 should remain 0 so that it remains in the n set. Got it? And similarly, we are making xp plus equal to 0. So you're making this guy equal to 0 so that it can go into the n set. The remaining x3 and x5 plus, they should remain greater than equal to 0. I mean, you can just assume greater because I'm calling this inactive and that one is active. In principle, greater and equal to 0. One is active, the other one is inactive. So the remaining two components, x3 plus and x5 plus, should remain greater than equal to 0 because you're making x1 plus equal to 0. Similarly, you're making x2 plus to be greater than 0, which means that x4 plus should remain equal to 0. That would ensure that your x plus, this along with this and this, will ensure that x plus is greater than equal to 0. Yes or no? Everybody with me? So what did we do? With this did the feasible part, and this was the basic part. The basic part was, now if you see, the B contains R indices because you're making this one and you're swapping the other one out, and you're also ensuring that xp plus is becoming equal to 0. So the n set is still containing active constraint, the complement of B, and you're also ensuring that the new B which you get after the swap stays non-singular. Everybody with me? That I was at one basic feasible point. By doing this little change, I went to the next basic feasible point. Yes or no? Now what we'll do is we'll make this concrete. Whatever I have written, I'll keep this on the board and we'll make this more explicit. What more explicit? How to choose xq plus, how to ensure all of this. What should I make xq plus? How should I make this equal to 0? How should I get this? 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 So that I get the new x plus. Right now I only have x. Everybody with me? Okay, so we'll work this out. This will remain. Let's not have this here, not to confuse you. But that's the swapping which I am trying to do. So we'll work this out one by one. So we'll start with the last one. Okay. So let's say this is ax is equal to ax plus. Can I split it into the b and the n components? So I can write this as b of xb plus n of xn. Well, was everybody who's here today in the lectures 2 weeks ago? This is what all we did more meticulously last time. Then I've not done the swapping yet. I'm still sticking with the same set of indices, but now what I want to do, I want to split it up. So I'll write this down as b of xb plus n of xn plus. Okay. I've not done any swapping at this stage. We are still sticking with this set of notation. I'm trying to find the next iterate such that I do something of this kind. So what I'll do, I'll split this guy into two sets. I'll call this as n tilde x plus n tilde plus aq xq plus. What I did was I separated this xq plus from this. And what is n tilde? N tilde is the n set complement of q. So if your n was 2, 4, the n tilde is now 4 because q is 2. Everybody with me? What do we know in this should remain 0? This of course is 0 because you're starting with the basic feasible point and you want to ensure that this also stays 0. x2 plus we are making greater than 0, but x4 plus should remain equal to 0. Everybody with me? So we will write this as b of xb is equal to b of xb plus aq xq plus, this implies xb is equal to xb plus s xb minus b inverse aq xq plus. Everybody with me? Sorry? What are you asking? 1 minute, I think this is, we write it more cleanly. Okay, what are you asking? Is we just separating, we have not done any swap of the indices right now. I just want to know what the next iterate is before doing the swapping, and it satisfies the basic feasibility. So I just use the same b and the same n, but I'm calling the iterates separately. xb, this is x and x plus. So x is xb xn and x plus is xb plus and xn plus. And in this one, xq plus is positive, while on the left hand side the xq is equal to 0. x2 was 0, but x2 plus is greater than 0. Yes or no? So what did we satisfy by doing this? We satisfied this, and we also satisfied this. I wish I had a colored, oh, there is a colored chalk. Unbelievable. We were able to satisfy these two things. What are we trying to do? Satisfy the 5 things of a basic feasible point so that we go from one to the next. Everybody okay? Now I have to somehow ensure this and this and this and this. All this I have to ensure and find the values, because I don't know what values I will get. So to do that, I'll explain you first with an example. I'll repeat this one more time if you're getting confused. This is the heart of Simplex. If you got this, then you're done. So we are in no hurry to do this. We'll repeat it again if you get lost. But once I tell you, I repeat it, and then when we do a problem, then it will be completely clear to you by the end of today's lectures. Okay, now let's do one thing. Let's look at an example. What I need to figure out first of all is how to make this guy greater than 0, so that everything else falls in place. That there is a p index in the b set which becomes 0. The remainder of the indices in the b set stay greater than equal to 0 or strictly greater than 0. This, after swapping, the b remains non-singular. The choice of xq plus is so crucial. So let's figure that out, how to get that. To do that, I am going to take an example and then tell you. Okay, let this be called a D. This is a vector, everybody agrees? What's the dimension of B? Quickly. R cross? R cross R, good. And what is AQ? R cross 1, it's the qth column of the A matrix. A matrix is R cross N, so the number of rows is still R, right? So this becomes an R cross 1 vector. Everybody with me? So it's a D vector, I am calling it for the moment. Let's do an example. Let's say you get some values of, and the problem which I am doing is this. It's a N is 5 and R is 3. And this was the set which I was carrying with me, just to explain you. Okay. So how many elements will XB have? 3, right? So let's say the values of that are 1, 2 and 3. Let's say, I'm just giving some trivial example. All these values are greater than 0. So by the way, if you recall the basic feasible point, again repeating 5 things: Ax equal to b, x greater than equal to 0. They exist a B set which contains R indices, the complement of B contains active constraint, and the matrix B formed from the columns of A with corresponding to the B indices is non-singular. At no point did I say that the elements, the xb's, can be strictly greater than 0. They can be greater than or equal to 0. But for the sake of instruction of this, I'll assume them to be strictly greater than 0. The case when some elements of xb become equal to 0 is called a degenerate case, which is one of the failures of simplex. So for the sake of simplicity with me, assume that B contains inactive and N contains active, rather than B containing both active and inactive. You know, it's not greater than equal to 0, it's strictly greater than 0. So we'll just stick to strictly greater than 0. Okay, for the moment. We'll come to this case when it's equal to 0 specifically. So I took a case when all are strictly greater than 0, minus, and let's say the D values, arbitrary values, come out to be 9, 8 and 12. And I don't know my xq plus. D will come out to be something. For the moment I have assumed to be all greater than 0, strictly greater than 0. I'll talk to you about the case when it is equal to 0 and less than 0 and so on and so forth. But this is for sure greater than 0. This will work out all the cases. So now tell me what should be the choice of xq plus such that this is satisfied and this is satisfied. How will you choose xq plus from that equation? Did you check वो वाला चल रहा है ना? हाँ देख लो ना ये now somebody shows up at 2:30 and then we are nowhere. So I want that one element of xb plus becomes equal to 0 and the remaining elements of xb plus take strictly greater than 0 or not equal to strictly greater than 0, because that's what we are trying to do. What should be this xq plus? And that xq plus has to be positive. It has to be positive. It should ensure this and it should ensure this. Correct. So what we'll do, we'll take ratio of everything. So we'll do ratio 1 over 9, this over this over this, and this over this. So this becomes 1 over 4. This also becomes 1 over 4. Okay? xbi divided by d, xb1 divided by d1, xb2 divided by d2, xb3 divided by d3. I did that. Now out of these ratios, I'll pick the minimum of that and call that as my xq plus. Why? Because if I take this as xq plus, then what will my xb plus will be? So this will be 1, 2, 3 minus 9, 8, 12 times 1 over 9. What do we get? 0, 2 minus 8 over 9, 3 minus 12 over 9. What did we got? Beautiful thing. We were able to make one index of the xb plus to be equal to 0, which we wanted, and we were able to get the remaining two indices to be greater than 0, which we wanted. Yes or no? So by this very nice choice of xbi divided by, so if you want to, so which index of the, what is p now? P is the index from the B set which we are kicking out. Is the first index of the B set. The first index of the B set turned out to be the first index of the overall set. You will come here 1, so this is 1. The second index of the B set is the third index of the overall set, and the third index of the B set is the fifth index of the overall set. So P is 1, and the remaining two elements, which are x3 plus and x5 plus, they remain greater than 0, which is this. Remove 1, 3 and 5. x3 plus is positive, x5 plus is positive, x plus 1 is equal to 0. Everybody with me? So by this very nice choice, let me erase this because this board is turning out to be less space for me. I don't want to erase any of these 5 things until I get you everything clear. So by this choice of x cube plus is equal to minimum di greater than 0 xbi divided by di. Huh?
It's not working.
Oh no, I hope nobody shows up here.
Actually, I think one professor has come also.
Oh, you have a lecture here? You mind taking it there?
But sometimes I see
No, it's my lecture only.
but 2:30 to 4
This one is free. The problem is that I have to do recording.
No, I can agree. But P4
Let me just check what's the availability. तुमने आज जो किया है ना मेरे साथ, where is my phone? Get my stuff from there. Okay. What was I saying? So by this choice of x cube plus, we were able to satisfy just one second, I don't want this. He's just checking whether his room is available till, what's the room number of that? 34.
So till 3:30 it is free, but after 3:30 someone booked the classroom.
Oh, acha, you've checked already.
Yes, I am just checking now. (2:30 to 3:30 it is vacant, sir. But after that,
Right. So just
One-
give me
one
few
and
more
half.
minutes, then let me finish it. Huh?
yeah, fine. Sir.
Yeah, thank you. Figure out, go. Figure the recording out. I'll finish it here. Okay. So what we did was, by this choice of x cube plus, we were able to get. We were first of all, are we getting this x cube plus greater than 0 by this choice? So the di's can be equal to 0 or less than 0, but I am picking only those di's which are greater than 0. Is xbi greater than equal to 0? It's greater than 0, yeah. Already said, no? It's a basic feasible point. Is di greater than 0? Yes, I am only picking the di which is greater than 0. So the ratio is greater than 0. So we were able to satisfy this guy. Right? Then we were able to make one index in the B set which we are referring to. So we'll call this I, the minimizing I, as the P. P is equal to I. The I which gives the minimum. Remember, in this case it came 1 over 9, 2 over 8, 3 over 9, 3 over 12, and the first element gave you the minimum value. So P became 1. So the minimizing I is called P. Right? So we were able to make one element equal to 0. So we were able to satisfy this. Correct? and then we were able to get the remaining two elements to be greater than equal to 0, so we were able to satisfy this. Yes? What did we not satisfy? Yeah, so this guy will automatically happen, which I'll show you in
So
the...
we'll continue to take this, or as move to L24. It is empty, yes.
Achha.
We can continue.
Thank you. I got so flustered now.
I'm really sorry.
I told you earlier, this happened before also, come early, check the cameras.
Till now is not figured out. That camera is not working.
I should not record, I should change my teaching anyways.
Yes.
That's what I should do now. It's more pain for absolutely no gain. Anyways, so where were we? Okay, so there's no hurry. So what we did was, what I'm saying is this choice of x cube plus is so powerful that it also ensures that when you do the swap of 2 and 1 in this example, p and q, the new b which will come out with the second, third and the fifth columns of A, or swapping this q going here and p coming here, that will remain non-singular. So by the end of lectures today, we'll prove that also. But what did we gain? Why were we doing all of this and what did we gain? We just went from one basic feasible point to the next basic feasible point. What was our goal? Our goal was to get all the mu's to be positive. We have no idea that this mu2 which we are trying to, of course the q will go into the B set, so the corresponding mu2 will become equal to 0. But the mu1 which will come in the 1 index which will move in here, the corresponding mu1, whether it will stay greater than 0, less than 0, equal to 0, we have no idea. And we have no idea whether the mu4 which was already negative, does it change anything or not. We know that it will remain equal to 0 because it's the, well, we don't know what will happen to any of those. So once this guy moves here, we will have no idea what will happen to mu1 and mu4. At this stage, we knew that mu2 was negative and mu4 was negative, and that is how we had picked the mu2 and we were doing all this work. But after the swap, what will happen to mu1 and mu4, we have no idea. The algorithm or the theory is not telling you that, but it does something more smarter. What it does, it says if you do all these steps, basically make x cube plus, and you go from one vertex to the next vertex of the basic feasible region, you will of course not ensure that the mu's which were negative are becoming positive, but you would ensure in the meantime that the function value is reducing, which means that you are moving towards the minimum, which we will see in an example today. Which means that if, let's say, at the first basic feasible point the value was 15, at the next basic feasible point the value would be less than 50, which means that by going from one vertex to the next vertex, you are slowly going towards the minimum value, although you are not ensuring that you are satisfying the necessary and sufficient conditions together. The mu's you have no idea. Once you keep iterating, you may get lucky that you will hit a vertex where all the mu's will become positive. Does it make sense? Yes or no? That I'll prove. That's what I'm saying. This part I have not shown you. I don't want to show this together because this is enough theory to tell you. I want you to do an example, then we'll come back to the theory. So the two theory questions which we'll answer. Let me use a different chalk. So one theory question which I have not answered is this guy, that this choice of x cube plus will also ensure that the new b becomes non-singular. What I have also not told you, that let's say if mu2 is negative and mu4 is negative, when you go to the next iterate and you look for your mu plus 1 and mu4 plus, you will have no idea that whether they become positive or not. They can still remain negative, both of them. But what this step will ensure is that your function value decreases. So after we do an example, I'm going to prove this and I'm going to prove this. so that you get the whole picture clear that why are we doing this. Is it making sense? So what I'll do, I'll now write the, should I repeat or everybody clear? I can summarize if you want. If even one person is not clear, please tell me. Aviral, you're doing something else. Okay. So scared. Okay. You're writing something, so I thought you're doing some other homework. Should I repeat one more time? Yes? So say it, there is no hurry. We have a lab after this. In the lab, you have to just implement the code. Like I said, the code for it is very small. You already did the initialization. The iteration is 5 more lines. It's not much. So coding will not take at all. It's not more than 1 hour's job. So we're in no hurry. So let's repeat this. I'll just emphasize certain things. Then we'll take a break. Come back, do an example. Then take a break. Then do the 2 theory questions. Is that okay? So by end of it, you should be, expert in Simplex now. Don't do a Google search on Simplex and start reading it. A disclaimer. Why? Because the Google search follows a tabular form where it doesn't go in this theory. As a computer science person, you need to know this theory. As an engineer, you don't know. So if you are an electrical engineer, I'll say, why to worry about this? No. It's not my job. It's given there, I'll just plug it in. But as a computer science person, you should know how to, at least know how to derive one constrained optimization algorithm. This is the only one we have done until now, right? So we'll just repeat it. So this was the initialization part. We had taken a basic feasible point, which is a vertex of a feasible polytope, and mapped it to the 5 necessary and sufficient conditions. All 4 of them, first 4 got satisfied, except the mu n, we had no idea. If your mu n's, all the components of mu n, what's the dimension of n? How many components does it have? N minus r, right? Because r are going in the B set, so the remainder has to go in the N set. So if n minus r components of the mu all turn out to be positive, you're good. The very first basic feasible point which is given to you was the solution and you're done. But if it is not, you iterate. So you pick any of the ones which are negative. It could be that some are positive, some are negative, some are 0. You pick the negative one because your goal is to work on that. Take the corresponding xq plus. Now we're calling this as xq plus because we earlier in the x iterate at the first basic feasible point. Now we're going to x plus the next basic feasible point. Make that value greater than 0. So which means if we had taken mu2, we would want x2 plus to be greater than 0. Now this earlier 2 and 4 were in the n set. Now you're making this greater than 0. It is no longer a basic feasible point. So this index has to be moved out and moved into the B set. So Q goes into the B set, correct? Now B can only contain R indices or 3 indices in this case. So one index has to be thrown out. That index, it comes into the N set, has to be an active constraint. So that has to be made equal to 0. When you do this swapping of 1 and 2, you have to ensure the new B matrix coming out of the A should remain non-singular. And you should also ensure that the other element in this one should stay 0, which is this guy, n complement q. The other elements inside the B set should remain strictly greater than 0. And you should also ensure that the feasibility is satisfied. So Ax is equal to Ax plus. Correct? So those are the 5 things which we have to satisfy. To be able to satisfy and figure out what that xq plus is, the very first thing we did was equate these two. When we equated these two, we split them into B and N sets. In this one, xn is anyway 0 because this was given to you. In this one, we are making xq plus out of the N set equal strictly greater than 0. So we separate the 2 out. So this is x2, this is x4 with the example which we are working on. We want to force this equal to 0. So we make this equal to 0 and we are left with this equation. Once we are left with this equation, multiply with B inverse and you get this guy. Now till this point I have not chosen. What I did was I satisfied this and I also ensured this by making this equal to 0. But there is a lot of unknowns which we still have to do. To do that, I said pick x cube plus to be the minimum of this index divided by this index, the value of that, which is xbi divided by di for all di's which are greater than 0. What does it ensure? It ensures that this stays greater than 0, because this is greater than 0 and we are picking the d's which are greater than 0, so we satisfy this. Once I substitute this guy into this, I am ensuring that ith component is becoming equal to 0. So in this case the first component is equal to 0 and the remaining components will remain greater than 0 because you are multiplying with a ratio which is lesser than their ratio. Make sense? So you were able to ensure this guy and you were also able to ensure this guy. What this choice also does is that after the swap, the new b stays non-singular, which we'll prove at the end. All this exercise also ensures that when you go from one basic feasible point and another one after the swap, the function value decreases. It does not ensure that the mu's in the next step will become, in the end set, will become greater than 0. Is that okay? Is better? So now one more thing. What if all the components of D are 0? Because this we know is greater than 0, I told you. Don't worry about equal to sign, that's a degenerate case which I'll tell you in the failures. But this D I have deliberately taken to be all positive. It could be that sum is negative, 1 is 0. Even if 1 is positive, you will take this guy and substitute and we go ahead with this. But what if all become 0 or all become negative? What happens in that case? If all become 0 or all become negative, that is a failure of the simplex algorithm. Which means at least one component has to be positive. It's called the case of an unbounded LP. I'll talk about that in failures case, which will happen in next week. And I'll explicitly tell you what are the 3 failures of simplex algorithm. Why you need to worry about interior point methods. For example, all those who are doing LP in the projects, no? I told you study about the interior point method if it is a continuous LP. If it's a discrete LP, that's a different story, right? But the discrete is an NP complete problem, so there is no efficient algorithm. So in case all are 0 and all are negative, there will be no you can't pick an x cube plus so that you make this component to be 0. Let's say this was -8, -12. You can no way choose an x cube plus positive so that you make one component 0. Because this is negative, this is positive, negative, negative, positive, you can always increase value. So you are stuck. So that's the case of an unbounded LP. Why it's called unbounded? Because you can infinitely keep decreasing the value of the objective function. You will keep going from one vertex to the next, but you will never find a minima. So that's an unbounded LP. There is no minima there. So we'll show that in that part. Everybody okay? Clear? Now if you have gotten this 80% okay, then 100% will become after the example. Is 80% okay? Okay. So we take a break, then we do an example. Take a break, then we do the 2 theory questions which are slightly more involved. Okay. You take a. Thank you. He went down. I had no idea what to do.
Can I stop there?
You stop it, then we start again.